Right, this is not log graphs as such. Okay, there's a different thing entirely on log graphs, and I'll put up another video for that. This is basically dealing with graphs that have logs as the axes. And there's two examples here, and you have to look very, very carefully at the example that you'd have to do, because what this one has is a log of base 10 of x and a log of base 10 of y axes. But the next one you're going to see is just going to have the one singular log axis, and it's just going to have a normal standard x axis, okay? And you can kind of tell the difference by the actual form of the equation that you asked to represent. So this one is y equals kx to the power of n, and the next one, the x, I'm pretty sure is going to be the index. Nonetheless, the actual work for the first part is exactly the same in both examples, okay? Basically what we want to try and do is we want to try and relate this form, y equals kx to the power of n, to the standard equation of a straight line, so y equals mx plus c. In other words, we don't want any powers, we kind of want a plus in there, and we want basically some form of multiplication to indicate the gradient somewhere, okay? So what we're basically going to do with this y equals kx to the power of n is we're going to apply laws of logs to introduce the fact that we've got a log of base 10y and a log of base 10x, and then play around with it until such a point as it looks something like y equals mx plus c. It's not going to look exactly like that because there's going to be logs in there, but it's going to have that kind of form. It's just instead of a y, it's going to have a log of base 10y, and instead of an x, it's going to have a log of base 10x, okay? So the first thing we want to do with that is basically take the log of base 10 of both sides. Okay, we can do that as long as we're doing the log of everything there. Right, now what we want to do is basically break up the right-hand side, because we've basically got our y-axis, and at the end of the day, if it's going to be y equals mx plus c, the y is indicative of the y-axis, so log base 10 of y on the left-hand side is fine. But the right-hand side is not quite how we want it, right? The temptation might be, using your laws of logs, to move the n to the front of this, but we can't do that because we're not finding, what's the kind of the base of that is just x. If there's brackets around the k and the x, then we can move the n to the front, okay? But because we've got this kind of multiplier, this k constant multiplied by the x to the power of n, I cannot move the n to the front because it's only to the power of the x. So my only other option here is to actually split up the k and the x to the power of n into two separate logs, okay? Obviously, if you had this kind of rule, this kind of thing, you'd combine them both together and you do k times by x to the power of n. So in the same way, we can split up kx to the power of n into two separate logs. And at this point, we can move the n to the front. Now, if we rearrange this, what you'll see is you've basically got something of the form y equals mx plus c. Okay, and if it is going to be y equals mx plus c, then we've got the different things for our different values. Obviously, in a straight line, we generally have the gradient and the y-intercept. So we've got them here. It's just that the gradient is going to be n, and the y-intercept is going to be log of base 10k. Okay, and as long as we know that, then we can do the second part. Okay, so we've shown that this graph represents the relationship of the form y equals kx to the power of n because we've basically shown that it's a straight line relationship using log of base 10y and log of base 10x instead of a standard y and an x. Okay, so now in part B, because we want to determine the values of n and k, we can use the version we've just expanded to find those things. We now know that n must be our gradient, and given the line and the points that we've got here, we can find a gradient. Okay, they're just standard points. Don't worry about the fact that they're different axes. We can find a gradient as normal by using the gradient formula. 0.3 is obviously a point. It's 0.3, so you've got your x value and a y value. Plug it into your formula, it comes out as 4. So the gradient is 4, so our n value must be 4. Likewise with a log of base 10k, log of base 10k is our y-intercept, okay? Those two things match up. And we know our y-intercept is just 0.3, okay? So we can say that log of base 10k must equal 0.3. And if log of base 10k equals 0.3, we rearrange that into exponential form, in which case k would equal 10 to the power of 0.3. Right, I know that might look like something that you should know or something that you should be able to do in your head, but it's not. You can shove that straight in a calculator. It's approximately 2, in which case we have our values for k and n, and we can actually rewrite in the original form y equals kx to the power of n. In other words, y equals 2x to the power of 4. Okay, right, obviously this is not a straight line graph. It won't look like a straight line graph unless we have logs as our axes, and that's kind of the point of this whole thing. As long as the axes are log of base 10y and log of base 10x instead of y and x, then it would be represented as a straight line. Okay? Right, so similarly for this example, so you're just kind of spotting the differences here. Yes, it's a negative gradient, but the main difference is the fact that this is just a standard x-axis. Okay, and as I say, the graph itself, what we're trying to actually represent, is a slightly different arrangement of what we had before. It's different letters, but the x, the main thing that we're looking at here, the connection between the y and x means that x is a power this time rather than the base in the previous one. But the actual first bit shows that this graph represents relationship is exactly the same. We're just going to go through it. We're going to take the log of base 10 of both sides. We're going to split up the a, b to the power of x. We're going to move to the x to the front. We're going to put it more into the form y equals mx plus c. But what you notice here is that the m is actually the log of base 10b, okay? The gradient is what we times basically the x coordinate by, or whatever our x equivalent axis is. It is just an x-axis here, and that's been multiplied by the log of base 10b this time. That's where it's different from the last one. In other words, our gradient is going to be log of base 10b. Our y-intercept is log of base 10a, okay? But this just obviously has a knock-on effect on the next part. And all it means is that we just have to do an extra logarithmic calculation. We can still use these 2 points to find the gradient, but it's just the fact that the log of base 10b is the gradient rather than the previous one. I think it was n was the gradient. So once we've actually found the gradient using the gradient formula, we have to go one step further to actually find b. If log of base 10b equals minus 0.4, then b will equal 10 to the power of minus 0.4. Again, shove it in a calculator, that's approximately 0.4. Now we can find a in exactly the same way as we did before, because log of base 10a is the y-intercept. We know the y-intercept from this diagram is 1.3. Rearranging that, a would equal 10 to the power of 1.3, and 10 to the power of 1.3 is approximately 20. Giving us our final form, y equals 20 times by 0.4 to the power of x. And just obviously be careful how you write that, okay? The only other thing to point out is these questions have been done nicely because they tell us, obviously, the point where it crosses the y-axis. We don't have to do any working for that. If it didn't tell us the point that where it crossed the y-axis, we'd have to work that out for ourselves, basically by going through the whole equation of a straight line, taking the gradient, y minus b equals mx minus a, rearranging it into y equals mx plus c, or substituting x for 0, and then substituting or then working out what the c value would actually equal. So maybe a one extra step, as I say, if it can I give you a point here and the point here rather than the y-intercept, then we'd have to go a little bit further. But nothing you haven't done before.